Hello students, in today's lecture we are going to learn about gravitation from NCERT section 7.9 to 7.10, and we will also solve two examples, that is 7.5 and 7.8. This is disclaimer. Learning objective: by the end of this session you will have a solid understanding of concept of earth, satellites, and energy of an orbiting satellite. So in today's lecture we will cover first 7.9 earth satellites, then we will solve an example 7.5. After that we will learn 7.10 energy of an orbiting satellite, and last we will solve again an example 7.8. All right. So 7.9 Earth satellites. So today we are going to explore the fascinating topic of Earth satellites. These are objects either natural like the moon or human made that revolve around our planet. So look at the figure here showing a satellite orbiting Earth. Satellite orbiting Earth like this, anti-clockwise direction. Look at here. This visual helps us understand the concept of revolution around a central body, which is a key aspect of gravitation. Motion of satellites. Their movement is quite similar to how planets orbit the sun. This similarity is important because it allows us to apply the same principles like Kepler's law to understand their behavior. Alright, keep in mind that these laws help us predict and explain the motion of celestial bodies. So, focus on Kepler's law of planetary motion. These laws are not just limited to planets, they also apply to satellites orbiting Earth. This means that the same rules governing the orbits of planets around the sun can be used to describe the paths of satellites around Earth. So, consider the shape of satellite orbits. So, they can be either circular or elliptical. The distinction is important because it affects the satellite's speed and distance from Earth at different points in its orbit. Alright, let's continue with motion of Earth satellites. Moon is Earth's only natural satellite. The figure shows the moon's orbit, which is important for understanding its movement relative to Earth. Alright, look at here. This is the movement of, look at here, relative movement relative to Earth. Keep this visual in mind as we delve deeper into its motion. The moon takes approximately 27.3 days to complete one revolution around Earth. This time period is significant because it influences various phenomena such as tides. Remember this, this is the moon's orbital period. The interesting thing here is this. Moon's rotational period about its axis roughly equal to its orbital period. This synchronization is why we always see the same side of the moon from Earth. It's a fascinating aspect of celestial mechanics because the moon's rotational and orbital periods are synchronized. The same side of the moon always faces Earth. This is known as synchronous rotation. And it's a key reason why the moon's appearance remains consistent from our perspective. Since 1957, technological advancements have allowed many countries, including India, to launch artificial satellites. This marks a significant leap in our ability to explore and utilize space for various purposes. Now we will focus on understanding the speed and period of a satellite as it revolves around Earth. When a satellite revolves in an elliptical or circular orbit around Earth, two forces acts on it. Alright. These forces helps satellites to maintain its stable circular orbit. The first force is gravitational force. The second force is centripetal force. Alright. So we are going to explore motions of satellites. So consider here a satellite of mass m revolving in a circular orbit at a distance of r is equal to re plus h. Alright, where re is the radius of Earth and h is height above Earth's surface. This distinction is important because it helps us calculate the satellite's orbit accurately. Now let's talk about the forces at play. The centripetal force that keeps the satellite in its circular path is given by the formula F is equal to mv square by re plus h. So the formula is this one, mv square by re plus h. Alright. So here we see the gravitational force on a satellite by Earth. This force is given by the equation F is equal to gme into m divided by re plus h whole square. In this equation, g is gravitational constant, me is the mass of the Earth, small m is the mass of satellites, re is the radius of the Earth, and h is height of the satellite above Earth's surface. For a satellite to remain stable in its orbit, the centripetal force required to keep it moving in a circle must balance the gravitational force pulling it towards Earth. This balance is expressed by the equation mv square by re plus h is equal to gme divided by m divided by gme into m divided by re plus h whole square. Here v is the orbital velocity of the satellite. This equation shows us that the satellite speed is important for maintaining its orbit. Let's see the orbital speed of the satellite. So we have v square is equal to gme divided by re plus h. Alright. So orbital speed of the satellite v is equal to under root gme divided by re plus h. This equation shows us that the orbital speed is directly related to gravitational pull of the Earth and inversely related to distance from the Earth's center. From this expression, we can observe that speed decreases as the height increases. This means that satellites further from the Earth move more slowly. Let's see the orbital speed at Earth's surface. So orbital speed at Earth's surface, so here h is equal to 0 from v is equal to under root gme divided by re plus h is v is equal to under root gme divided by re. So now let's simplify this using the acceleration due to gravity g. So we can say g is equal to gme divided by re square. So we can rewrite our orbital speed formula as v equal to under root gre. Alright, and this shows us how gravitational acceleration and Earth's radius determine the orbital speed. So let's substitute the values for g and re into our equation. We have g equal to 9.8 meter per second square. Re is equal to 6.37 into 10 raised to the power 6 meters. So v is equal to, solving this, you will be get 7.9 kilometer per second. This is the speed an object would need to maintain to orbit the Earth's right at its surface, which is quite fast. Now we are going to explore the relationship between orbital speed and escape speed. So let's start with orbital speed, which is the speed an object needs to stay in orbit around Earth. The formula for orbital speed v naught is equal to under root gre, where g is acceleration due to gravity and re is the radius of the Earth. So we have escape speed, which is the speed required for an object to break free from the Earth's gravitational pull without any further propulsion. So v is equal to under root 2 gre. So now let's compare these two speeds. We can express escape speed as ve is equal to under root 2 into under root gre. Alright. So ve is equal to under root 2 into v naught. Escape speed is root 2 times the orbital speed near the Earth's surface. Now we are going to explore the concept of orbital period of a satellite. Our aim is to understand how long it takes for a satellite to complete one full orbit around the Earth. This is a fundamental concept in understanding satellite motion and its applications. So let's start by defining the orbital speed period. The orbital period is the time taken by a satellite to complete one revolution around the Earth. So mathematical analysis. The formula for the orbital period is given by t is equal to distance covered by the satellite divided by orbital speed of satellite. This equation shows us that the orbital period depends on both the distance the satellite travels and its speed. So we can express the orbital period more specifically as t equal to 2 pi r divided by v naught. Here 2 pi r represents the circumference of the satellite's orbit and v naught is the orbital speed, where r is the radius of the orbit and v naught is the orbital speed. Let's see the orbital period. So let's begin by the substituting the expression for the orbital velocity. V naught is equal to under root gme divided by r into the formula for the orbital period, that is t equal to 2 pi r divided by v naught. So now observe the resulting equation, t is equal to 2 pi r divided by under root gme divided by r. This equation shows how the orbital period depends on the radius of the orbit and the gravitational constant. Squaring both sides, we get t square equal to 4 pi square r cube divided by gme. This equation is significant because it directly relates the square of the orbital period to the cube of the radius. highlighting a fundamental principle in orbital mechanics. This result aligns perfectly with Kepler's third law, which states that T square is proportional to R cube. This law is a cornerstone of celestial mechanics, showing how the motion of planets and satellites is governed by predictable mathematical relationships. Let's continue with orbital period. So let's start by considering a satellite that revolves around Earth in a circular orbit. The radius of this orbit is given by r is equal to re plus h, where re is the Earth's radius and h is the height of the satellite above the Earth's surface. This forms the basis of the calculating the orbital period. So substituting r is equal to re plus h in t square equal to 4 pi square divided by gme into r cube. So it will be t square equal to 4 pi square divided by gme into r plus h whole cube. This equation shows us how the orbital period depends on the radius of the orbit. So simplifying and substituting constant, you will be get t square. So we know 4 pi square divided by gme is equal to k. So t square equal to k into re plus h whole cube. This simplification helps us see the direct relationship between orbital period and the orbit's radius. So when a satellite is very close to the Earth's surface, the height h can be neglected compared to the Earth's radius re. So hence for such satellites, by substituting h is equal to 0 in t square equal to 4 pi square divided by gme into re plus h whole cube. By doing this, we simplify the equation to focus on the Earth's radius alone, which is important for satellites in law of Earth's orbit. For h is equal to 0, t will be written as t naught. So t naught square equal to 4 pi square re cube divided by gme. So t naught is equal to 2 pi into under root re divided by g. Alright. If we substitute the numerical values, g is approximately equal to 9.8 meter per second square and re is equal to 6400 kilometer, and we get t naught is equal to 2 pi into under root 6.4 into 10 raised to the power 6 divided by 9.8, which is equal to 85 minutes. This calculation gives us a practical understanding of how long it takes for a satellite to orbit Earth when it's close to the surface. Example 7.5. The planet Mars has two moons, Phobos and Deimos. Phobos has a period of 7 hours 39 minutes and orbital radius of 9.4 into 10 raised to the power 3 kilometer. Calculate the mass of Mars. Assume that Earth and Mars move in circular orbits around the Sun, with Martian orbit being 1.52 times the orbital radius of the Earth. What is the length of the Martian years in days? Alright, let's see the solution. So let's start by identifying the given information in the problem. So Phobos orbital period is equal to 7 hour 39 minute. Phobos orbital radius 9.4 into 10 raised to the power 3 kilometer. In meter it will be 9.4 into 10 raised to the power 6 meter. And Mars orbital radius Rm is equal to 1.52 Re, where R is the Earth's orbital radius. G is equal to 6.67 into 10 raised to the power minus 11 Newton meter square per kg square. Alright. Converting the time period from hours to seconds. So we have t equal to 7 hour 39 minutes. So t is equal to convert the time, we multiply hours by 60 to get minutes, and then by 60 again to get seconds. Similarly, we convert minutes directly to seconds. So we have 7 times 60 into 60 plus 99, 39 plus 39 into 60. So solving this, you will be get t is equal to 27,540 seconds. It's important to ensure our units are consistent for accurate results. All right. So let's begin by applying Kepler's third law to find the mass of marks. So the formula we use is t square equal to 4 into pi square into r cube divided by g me. All right, where t is the orbital period and r is the orbital radius. Capital G is gravitational constant. This equation shows the relationship between orbital period and the mass of the central body. Substituting the values, r equal to 9.4 into 10 raised to the power 3 kilometer, and the value of g, you will be get the m. So m equal to 4 pi square into 9.4 into 10 raised to the power 6 whole cube, and divided by 6.67 into 10 raised to the power minus 11 into 27,540 whole square. Solving this, you will get 6.42 into 10 raised to the power 23 kg. This result gives us an idea of the scale of planetary masses and how they can determine using data. Alright. Now, calculating the length of a Martian year using Kepler's third law, which states that the square of the orbital period is proportional to the cube of the orbital radius. This law helps us relate the time it takes for a planet to orbit to the Sun to its distance from the Sun. So comparing year length at Earth and the marks, so you will be get Tm square divided by Te square equal to Rm cube divided by Re cube. So simplifying, Tm is equal to Te into Rm divided by Re whole power 3 by 2. Alright. Now substituting the given values into the formula for the Martian year, Rm is equal to 1.52 Re and Te is equal to 365.25 days. In the formula, Tm is equal to Te into Rm divided by Re whole power 3 by 2. So you will be get Tm is equal to 365.25 into 1.52 whole power 3 by 2. So Tm is equal to 365.25 into 1.87. Solving this, you will be get 684.5 days. Therefore, the Martian year is approximately 685 Earth days. Now, we are going to understand the energy carried by an orbiting satellites. We will explore how satellites in orbit possess both kinetic and potential energy. This foundational understanding will help us analyze the dynamics of satellites and their energy states. Considering a satellite revolving in an orbit with a certain speed v, this satellite possesses both kinetic energy denoted as k and potential energy denoted as u. So kinetic energy is k equal to half mv square, where m is the mass of the satellite, v is the speed of orbital speed. So we can further express the kinetic energy by substituting the expression for orbital speed. So k equal to 1 by 2 m into gme divided by re plus h, because we know b is equal to under root gme divided by re plus h. So simplifying the expression, we get k is equal to gme m divided by 2 into Re plus H. Let's continue with energy of orbiting satellite. So let's focus on the potential energy. As U, the formula for potential energy U equal to minus of Gme into m divided by Re plus H. Alright. And the total mechanical energy E is the sum of kinetic energy Gme into m divided by 2 into Re plus H. And the potential energy E is equal to K plus U. So E equal to Gme into m divided by 2 into Re plus H plus minus of Gme into m divided by Re plus H. So solving this, you will be get E equal to minus Gme into m divided by 2 into Re plus H. This results shows that the orbital mechanical energy of an orbiting satellite is negative, indicating a bound system. Let's continue with energy of an orbiting satellite. So the general expression for the total energy of a satellite, the formula is E equal to minus Gme into m divided by 2r. Here E represents the total energy, G is the gravitational constant, Me is the mass of the Earth, and m is the mass of the satellite. Small r is the distance from the center of the Earth to the satellite, where r is equal to Re plus H. Also, for the energy of a satellite near Earth's surface, H can be neglected in E equal to minus of Gme into m divided by 2 into Re plus H. So by neglecting H, the equation simplifies further to E is equal to minus Gme into m divided by 2 Re. This simplification helps us understand the energy of satellites that are very close to Earth's surface, where the altitude has minimal impact on the total energy calculation. So let's continue with energy of an orbiting satellite. So some key observations. So we found that E is equal to minus Gme divided into m divided by 2r, and kinetic energy K equal to Gme m divided by 2r, and potential energy minus Gme into m divided by r. So total energy is negative, which is a characteristic of a bound system. This negative energy indicates that the satellite remains trapped within Earth's gravitational field and cannot escape. If the total energy were to become positive or zero, the satellite would gain enough energy to escape Earth's gravitational field and travel to infinity. Total energy equals to the kinetic energy E equal to minus K. This relationship demonstrates the balance between the satellite's motion and its gravitational binding. So finally, note the important relation, the energy, total energy equals to the half of the potential energy equal to U by 2. This relationship further emphasizes the interconnectedness of the energies involved. It's a mathematical result that shows how potential energy is distributed in a bound system. A 400 kg satellite is in a circular orbit of radius 2 Re about Earth. How much energy is required to transfer it to a circular orbit of radius 4 Re? What are the changes in kinetic and potential energies? Let's see the solution. To solve this problem, we need to recall some important formulae related to gravitational forces and energies. These will help us understand the forces acting on the satellite and the energy changes involved. So first, gravitational force Fg is equal to Gmm divided by r square, and centripetal force Fg equal to mv square by r. Kinetic energy half mv square. Potential energy minus Gmm divided by r. Total energy sum of kinetic energy plus potential energy. Alright. Satellites in a stable circular orbit, which means the forces acting on it are balanced. specifically the gravitational force pulling it towards Earth, is balanced by the centripetal force needed to keep it moving in a circle. The gravitational force is given by the formula Gme into m divided by r square, where g is the gravitational constant, is equal to mv square by r. So from equation we just derived, we can solve the satellite's velocity v square is equal to gme divided by r. So next, let's calculate the kinetic energy. That is, the formula is 1 by 2 mv square. By substituting the expression, we found v square. All right. So we substitute the expression for the velocity. So v square equal to gme divided by r in the formula of kinetic energy, that is half mv square. So we get k is equal to 1 by 2 m into gme divided by r. So kinetic energy is equal to negative of 1 by 2 potential energy. All right. Now first, let's consider the total energy of satellite, which is the sum of its kinetic energy Ke and potential energy Pe. So Ke energy is equal to minus 1 by 2 Pe plus Pe. So E is equal to potential energy divided by 2. This shows us that the total energy is half of the potential energy, which is a key concept in orbital mechanics. So now let's express the total energy in terms of gravitational parameters. So we have E equal to minus gme into m divided by 2r, where g is the gravitational constant. All right. Now, first let's calculate the total energy for both initial and final orbits. So total energy in an orbit is the sum of kinetic and potential energy. This will help us understand the energy changes involved in moving the satellite. Initially, the satellite is in orbit with radius of 2 times the Earth's radius. This is our starting point for calculating the total energy. Remember, the radius is a crucial factor in determining the gravitational energy. So to calculate the total energy, substituting R is equal to 2 times of Re in E equal to minus Gme into m divided by 2R. So E1 is equal to minus Gme into m divided by 4Re. For the final case, satellite was in orbit of radius r equal to 4 times of Re. Total energy in this case is E2 is equal to minus G into m divided by 8 Re. Now, energy required for transfer from initial to final orbit, we will equal to the change in total energy. So the change in energy, denoted as delta E, is calculated by subtracting the initial energy E1 from the final energy E2. So we have delta E is equal to E2 minus E1. So delta E is equal to minus Gme into m divided by 8 Re plus Gme into m divided by 4 Re. So delta E is equal to Gme into m divided by 8 Re. Substitute the known values into our equation. So we have delta E is equal to 6.67 into 10 raised to the power minus 11 into 5.97 into 10 raised to the power 27 into 400 divided by 8 into 6.37 into 10 raised to the power 6. All right. So let's solving for the change in total energy. So delta E is equal to 6.67 into 5.97 into 4 into 10 raised to the power 26 minus 11 divided by 50.96 into 10 raised to the power 6. So delta E is equal to 159.28 into 10 raised to the power 15 divided by 50.96 into 10 raised to the power 6. delta E is equal to 1.56 into 10 raised to the power 9 joule. All right. So using the general formula for orbital kinetic energy, Ke is equal to Gme into m divided by 2r. Kinetic energy for initial and final orbits, Ri is equal to 2 times of Re and Rf is equal to 4 times of Re. Can be written as K is equal to Gme into m divided by 2 into 2Re is equal to Gme into m divided by 4Re. So final kinetic energy is Gme into m divided by 2 into 4Re. Solving this, you will be get Gme into m divided by 8Re. All right. So now let's focus on the change in kinetic energy. So change in kinetic energy is final kinetic energy minus initial kinetic energy. So solving this, you will be get Gme into m divided by 4Re into 1 by 2 minus 1. So change in kinetic energy is equal to minus Gme into m divided by 8Re. So it will be negative of change in total energy. Since we have already calculated the delta E equal to 1.56 into 10 raised to the power 9 joule, we can conclude that delta E is equal to delta Ke is equal to minus 1.56 into 10 raised to the power 9 joule. This tells us that the kinetic energy decreases by the amount as the satellite moves to the higher orbit. All right. Now, by using the general formula for the orbital potential energy for the initial and final orbits can be written as potential energy initial is equal to minus Gme into m divided by 2Re, and potential energy final is equal to minus Gme into m divided by 4Re. So change in potential energy, final potential energy minus initial potential energy. So change in potential energy is equal to minus Gme into m divided by 4Re minus of minus Gme divided by into m divided by 2Re. So simplifying the expression, we get delta Pe is equal to Gme into m divided by 2Re into minus 1 by 2 plus 1. So change in potential energy is equal to Gme into m divided by 4Re is equal to 2 times of delta E. So delta P is equal to 2 times of change in total energy. So delta P equal to 2 into 1.56 into 10 raised to the power 9. So it will be 3.12 into 10 raised to the power 9 joule. All right. Therefore, we get energy required to transfer circular orbit of radius r is equal to 2 times of Re to r equal to 4 times of Re. So just put the values and calculate the energy. So change in energy is equal to minus change in kinetic energy is equal to minus 1.56 into 10 raised to the power 9 joule, and change in potential energy is equal to 3.12 into 10 raised to the power 9 joule. Before we end today's lecture, let's quickly go through the summary of the what we have learned. Earth's satellites are objects revolving around Earth in circular elliptical orbits following Kepler's law. Moon is the Earth's only natural satellite with a period of 27.3 days. For stable orbit, centripetal force equals gravitational force. That mv square by r is equal to gmm divided by r square. So orbital velocity v equal to under root gme divided by r decreases with increasing height. Escape speed is root 2 times orbital velocity. So ve is equal to root 2 v naught. Orbital period t square equal to 4 pi square divided by gm into r cube. And total energy of satellite E equal to minus gmm divided by 2r, negative for bound orbits. For elliptical orbits, energy depends on semi-major axis E equal to minus of gmm divided by 2a. And kinetic energy equals to the half of potential energy magnitude. K is equal to minus U by 2. Now we have some practice questions. These will help you revise today's concepts and build your problem solving skills. And most importantly, solving these questions will help you a lot in your exam preparation. First question: a satellite orbits Earth at height h above a surface. If Earth's radius is r, find its orbital period in terms of g, r, and h. If a satellite's velocity at Earth's surface is v, what is its escape velocity? A satellite has total energy E in orbit. Express its kinetic energy in terms of E. Calculate orbital velocity of a satellite at height h, height 2r above Earth's surface, where r is the Earth's radius. If a satellite's potential energy is U, what is its total mechanical energy? All right. Thank you for your attention.